Stars can be classified by various measures, including magnitude and temperature. The most popular classification is the Morgan-Keenan spectral classification, as shown in this animation. These classes, ranging from M to O, are in order of increasing magnitude and temperature. The star in this animation changes colour from orange in class M, through white in class F, to blue in class O. Most of the output of a class O star is ultraviolet. Our Sun is in class G, as are 1 in 33 other stars.
A black body is an object that absorbs all electromagnetic radiation that falls upon it. This means that no radiation passes through it or is reflected off it. If the black body is above 0 degrees Kelvin, which is minus 273 degrees Celsius, then it will emit the radiation absorbed as thermal radiation or heat. The radiation emitted will have a peak wavelength and intensity at different temperatures. A hole is a perfect black body. Any radiation which goes into it is absorbed. It emits radiation when it gets hotter. The best natural black body is carbon. Classical theory of radiation from black bodies, the Rayleigh-Jeans law, was proved wrong by Max Planck and Wilhelm Wien. Classical physics hypothesized an infinite intensity for very small wavelengths, but the introduction of Planck's constant proved this wrong. This showed that at different temperatures, the peak intensity was at different wavelengths. This intensity also varied with temperature. This theory can be related to stars and why they look different colours. Hotter stars appear bluer than colder stars, which appear red. As the graphs show, as the temperature increases, the peak wavelength moves towards the left, showing that it is getting shorter. At 3000 Kelvin, the peak wavelength is off to the right of the visible light spectrum, therefore we see the star as red. At 6000 Kelvin, the peak wavelength is right over the visible light spectrum, or the wavelength, therefore it appears white. As the temperature increases to 10,000 Kelvin, the peak wavelength is now shorter than the visible light, thus the star appears blue. The equation needed for this is lambda max T equals 0.0029 meters Kelvin. The equation can be used to calculate the maximum wavelength emitted by a black body. This equation and the constant 0.0029 meters Kelvin, also known as Wien's displacement constant, are given on the formula sheet.
The power radiated by a black body increases rapidly with temperature. If you double the temperature in Kelvin, it means that the power radiated by each square meter is 16 times greater. The graph shows how the power radiated by a surface is affected by the temperature. We can use this to calculate the luminosity of a star. The Sun, as you can see, has a temperature of 5800 Kelvin, and using the graph we can see it radiates 6.5 times 10 to the 7 watts per meter squared. The Sun has a radius of 6.96 times 10 to the power of 8 meters, so its surface area is 6.08 times 10 to the 18 meters squared. Luminosity equals power emitted per square meter multiplied by the surface area, so for the Sun this equals 4 times 10 to the power of 26 watts. The luminosity of a star is the total power it radiates. The luminosity depends on both the power per square meter and the surface area of the star. To calculate a star's luminosity, you must first 1. Determine the wavelength at which the maximum intensity occurs using the spectrum. 2. Use Wien's law to determine the temperature. 3. Determine the power emitted per square meter. And 4. Calculate the radius of the star.
All stars begin here at the start of the main sequence stage as a mass of gas producing energy for the fusion of hydrogen and small amounts of helium. If the star is of a relatively low mass, then it will continue along this path as a main sequence star, gradually getting hotter and more luminous over billions of years. Over 80% of stars fit into this category. When the star runs out of hydrogen, helium, and any other elements it can burn in its furnaces, the star collapses in on itself due to its own gravity, becoming a small and dense white dwarf. If the initial mass of the star is large enough, then when it reaches approximately 5000 Kelvin on the surface, it will become a red giant. These are cooler than the Sun, so emit less energy per square meter of surface. However, they are more luminous than the Sun, meaning they must have a much larger surface area and so a larger diameter, hence the term giants. If a star has a large enough initial mass, then it can turn into a supergiant. Supergiants are enormous and very bright. The supergiant will emit about 90,000 times the energy of the Sun, meaning it will have a diameter roughly 300 times that of the Sun.
The Sun used to be smaller. The present-day Sun is this size. In 1 billion years, the ice caps will melt away, and after another 500 million years, the oceans will boil, and the atmosphere will be removed by the ever-increasing solar winds. The Sun is now in the red giant sequence. It will rapidly expand, engulfing Mercury and then Venus, whilst turning the Earth into nothing more than a ball of molten rock. The Sun then rapidly shrinks as the hydrogen supply is exhausted. For many millions of years, the Sun will burn only helium. When the helium runs out, the Sun explodes as a planetary nebula, and then implodes into a white dwarf slightly smaller than the Earth. It remains in this state until the end of time.